Hello everybody. Welcome to this webinar on recycled aggregates, overview and prospects. My name is Mark Alexander from the University of Cape Town. I'd like to acknowledge the contributions of others, PhD students Arij Khamildin and Iche Amadi, Hans Boyshausen and others. I'd also like to acknowledge the contributions of Indian Institute of Technology Madras, IITM, and our colleagues there, with whom we have collaborated on this topic for a number of years. This is what I'd like to cover: circular construction, and then construction and demolition waste, or is it a resource? Then processing and beneficiation techniques, recycled concrete aggregates, something on their composition and properties, uses in industry and quality control, standards, and challenges and prospects. This is the current situation in construction in most of the world. Linear construction. Although this is a circular diagram, in fact it's a linear system, because from raw material extraction through the construction phase and then the deconstruction phase, we'll end up in the landfill, and that's a linear system. This is no longer acceptable. We need to move to a circular construction system where, at this stage at least, we intercept the waste stream, process and beneficiate it, and turn it into useful materials. In this case, possibly recycled aggregates. We could, of course, stop at this point and deconstruct the system and even use whole structural members again, but this system is now required. And here's a definition of the circular economy, or circular construction, if you like. The circular economy is a multi-level resource use system that stipulates the complete closure of all resource loops. Recycling and other means that optimize the scale and direction of resource flows contribute to the circular economy and supporting practices and activities. In its conceptual perfect form, all resource loops will be fully closed. In its realistic imperfect form, some use of virgin resources is inevitable. And I acknowledge Johan Vinker for that quotation, past president of Rilem. We might also be well aware of this diagram from the Globe Consensus, where circularity is defined. Here's sustainable construction. These are the elements that contribute to sustainable construction, and the other aspects here around durability and so on and so forth. What we need in the end is functional, durable, and resource-efficient concrete, including use of recycled aggregates. So let's talk about construction and demolition waste. It's the non-hazardous waste produced during the construction, repair, rehabilitation, or demolition of infrastructure. And it is a variable composition. Usually it's some sort of mineral waste or building rubble, but that contains, for example, clay bricks, wood, possibly plastic, and usually metal of some kind, and so on. Importantly, it's estimated at 10 to 30% of total waste globally. That's a huge number. This depends on the country or the region. There is an estimate of about 3.33 billion tons of global CDW annually, again a large number. And taking the EU in 2016 for an example, of the total of about 2.73 billion tons of raw aggregate that was consumed then, only about 8% comprised recycled aggregates. So clearly there's room for improvement here. But waste here really is a resource, and if we begin to view it as a resource, it leads to a new mindset. For example, the stimulation of a secondary resource economy based on the recovery of material and energy resources from that waste. Also, it's a resource because in this sense we reduce the waste sent to landfill, and we reduce the exploitation of non-renewable resources, and we have the improved efficiency of material resource flows. Turning to South Africa and CDW in our country, around 4.5 million tons is produced annually, but this could be as high as 10.8 because these numbers are somewhat unreliable. And as of 2017, only about 19% was recovered or reused. But turning to the Western Cape in particular, and Cape Town, which is where I live here, in 2017, about 30 to 40% of this amount was recovered, whereas in 2022, that jumped to somewhere close to. And that is clearly seen in this slide here, where up to 2017 or so, this was the amount of received waste at the Cape Town landfills, whereas it dropped to these numbers after 2018 or 19. And the simple reason was, well, there were two reasons. First of all, the city required a demolition certificate from every owner or whoever was demolishing a building, in which they had to indicate what they would do with the demolished material, indicating reuse. And secondly, the gate fees for the landfill sites were largely increased. And so within the space of a year, this situation was turned around. So it's interesting to see what can be done with proper legislation, with proper regulation, and with proper motivation. Now, with regard to processing and beneficiation techniques, we start, of course, with the collection of C&DW. And this is an illustration of Chennai in Tamil Nadu in India, the city, where in fact I've just come from spending 3 weeks with colleagues there. And these dots here represent the waste generation points in Chennai in 2013. And you can immediately see the problem. There are multiple sources of C&DW throughout the city. And so it's very difficult to collect this economically. What is really required is for the local authority to designate maybe half a dozen or maybe a dozen collection points where people are required to take the C&DW. And from there, one can actually make use of it much more easily than trying to collect it over such a wide and dispersed area. That then, of course, one needs to separate it. And here's an example from our own city. There are the mountains in the background, where here you can see some mixed waste. Here is some more or less concrete waste here, but some soil over there. And so really what you want to do is to separate at source and not include this in your recycling material. Once you've done primary crushing, normally this would be a jaw crusher, which breaks down the large particle sizes, and also removal of contaminants. In this case, you can see the steel here reinforcing that has been removed, and of course itself can be recycled. There are certainly other contaminants that may need to be removed, very often indeed by hand. One then moves to secondary crushing, and this is also an example from our own situation. Here is a secondary crusher, and that is now, maybe it could be a vertical impact crusher or something similar that allows better separation and better particle shape to be. And then into sieving. So here is a mobile crusher. Here is a sieving, a mobile sieving machine, where from the crusher, the stream is then separated into, in this case, coarse aggregate over there, or recycled aggregate, and the fine material landing up over there. So we land up with stockpiles of various grades of recycled concrete aggregates. Example of what I mean. Here are 3 examples of coarse recycled concrete aggregate as a function of particle size. And here's the fine recycled concrete aggregate that also comes from the process. And what is common to all of this is what we call the adhered paste or the adhered mortar, and there are varying amounts of this in the recycled material. And this is the issue that we have. And there are 2 processes that we can use to try and improve or beneficiate the recycled concrete aggregates. There's the removal of the adhered mortar, because it is a problem, or there's the surface modification of the recycled concrete aggregates. Thirdly, there's also mineralization, but I won't deal with that in this presentation. So here are these first 2 strategies, the removal of adhered mortar or surface modification. In the first case, one can do mechanical scrubbing, acid soaking, not a particularly good idea, microwave heating, conventional heating, or possibly ultrasonic water cleaning. That's also not a very useful idea. On the surface modification side, one can add pozzolanic materials to try and utilize some pozzolanic reactions, the possibility of adding of nano materials, biodeposition or carbonation. This is more the mineralization route, which I'm not going to speak about now. But here's an example, just a simple Los Angeles abrasion machine with this material, once it's been through this LA machine, can turn into this material, which to all intents and purposes, is very similar to virgin aggregate again. Now, the composition of RCA is important. As we've mentioned, there is the presence of the adhered mortar. But here you can see, first of all, the hardened cement paste phase over here. Then there's unhydrated cement, possibly up there. Homogeneous natural aggregate here. But usually it exists here as a combined particle. So you have some original aggregate and some adhered mortar with possibly even a little bit of unhydrated cement in there as well. And the consequence of that is that you have multiple interfacial transition zones, and these have a large influence on the mechanical and engineering properties of the material. So what we know then is that there's high material variability, and this affects. So the composition then depends on the properties and composition of the parent concrete, the crushing procedures, and the number of crushing stages, and the end particle size of the recycled concrete aggregate. And here we see that as the particle size reduces, you get more of this adhered mortar. Here's a micrograph of the situation. There, in fact, is the adhered mortar here and the original aggregate particles. And if you just look at this section here, here is the original aggregate with some adhered mortar sticking to the surface and a whole lot more over here. And this is the material that we have to handle in terms of beneficiation. And so if we compare recycled concrete aggregate with natural aggregate, we find that it has higher porosity. That's due to the adhered mortar, lower density, higher water absorption, and higher abrasion loss. And as I've said, all due largely to the cement paste phases, including the ITZ phases. And here again, there's a comparison of coarse RCA with fine RCA. In this case, less adhered mortar, higher density, lower water absorption, contains less contaminants, used for structural concrete applications in most standards. Whereas here we have the higher adhered mortar content, lower density, higher water absorption, contaminant content may be higher, and presently this material is quite restricted in most standards. And here is an illustration of some of those points. Here we are plotting absorption versus maximum aggregate size. And although there's a large scatter of data here, there's a clear trend that as the maximum aggregate size increases, so the absorption comes down. Now, for normal crushed hard rock aggregates, bear in mind that the absorption is typically a maximum of around 1%. Normally in South Africa with our hard rock crushed aggregates, we're at around about 0.5%, so quite low. So even with this size of aggregate here around 2025, you can see that the absorption can be considerably higher than natural virgin aggregates from hard rock, crushed from hard rock. This is also illustrated here where we have these frequency plots of recycled aggregate versus natural aggregate. And in the specific gravity or relative density plot, obviously the natural aggregate has higher relative density, whereas the recycled aggregate lower. And the other picture in terms of absorption. Here, the natural aggregate has low absorption, the recycled aggregate has relatively high absorption. This is also well illustrated in this diagram with absorption versus specific gravity or relative density from a whole series of studies. And here you can see, for example, that the natural aggregate, coarse natural aggregate, falls down here in this area. We then have, this is the coarse recycled aggregate, higher absorption, lower relative density. And so we move up to, for example, the fine recycled aggregate up in this region here, which has got high absorption and low relative density. Now, structural engineers are always interested and concerned about compressive strength. So what does that mean? Well, here you can see, again, a high variability of results from a series of references. But the important thing to note is that in many cases, or certainly in some cases, it's possible to get very little reduction in compressive strength of the final concrete, even at 100%, and this is coarse recycled aggregate replacement. On the other hand, you can see this plot here, or even some of these, there can be a very substantial effect on compressive strength, which is obviously what we don't particularly want. fine recycled aggregate, the same picture emerges, although the data is more sparse. Here you can see again that it's possible to, even at 100% replacement, get reasonable figures for reasonable values for compressive strength, but at the same time it's possible to get large reductions in compressive strength. And so what this tells us is that every case needs to be considered on its merits and has to be judged accordingly. Here is an example of a thermomechanically treated coarse aggregate from IITM. This is where you virtually remove all the adhered mortar by thermomechanical treatment. And here you can see that for 3, 7, or 28-day strength results, there really is very little difference, and this aggregate is, to all intents and purposes, similar to the original aggregate itself. This is coarse aggregate, of course. Now, here's the approach that we've tended to take at UCT, where we've treated the fine recycled aggregates with, in this case, fly ash and slag. Here, fly ash. And here again, compressive strength, and you see 3, 28, and 180 days. Again, you can see that at 180 days, really, there's not a lot of penalty to pay. In this case, using 50% fly ash, a 50% replacement, in a fly ash concrete. And you can see the same in the early strengths, a little bit lower here. If we then look at the OPI, or the oxygen permeability index, of plain concrete and fly ash mixes here, this is actually, again, a fly ash mix with up to 50% replacement. And the OPI is here again. There is a little reduction, but not substantially so. In other words, we're able to make up to 50% replacement here of the natural aggregate and still get very good properties. And again, this can be seen even at 28 days here. Bear in mind that anything with a value over about 10 OPI is actually a very good concrete from a permeability or penetrability point of view. If we look at the chloride conductivity index of plain and GGBS or slag mixes, the same picture emerges. The slags, of course, have very substantial effects on bringing down the chloride conductivity, as we know. But the recycling of the aggregate here also has, fine recycled aggregates in this case, has no major detrimental effect, even up to about 50%. So it's possible to do this. This is good, and these are excellent. Here is something on carbonation depth and 2 different water binder ratios. And obviously it's as you would expect, the lower water binder ratio giving you the lower values. And again, the carbonation depths are not adversely affected at these different ages by the use of, in this case, fine recycled aggregate at up to 50% replacement. So, what about use of these materials? Well, they can be used in high and low strength concretes. Here's a high strength application, a typical column and slab structure in which these materials can certainly be used, provided that they're properly beneficiated and the properties are understood. However, in many cases, these materials land up in this type of application, brick and block construction. And particularly in the developing world, where up to 80% of cement usage actually goes into these kinds of applications. This is an eminently useful and suitable use for these materials, because here the strengths are lower and therefore quality is less important, although of course not unimportant, but it's an eminent use of this material in this kind of construction. But bear in mind there are other possible uses: landscaping, embankments, fill or hardcore material, other construction, or pavement construction. And here you see an example of a road base from recycled concrete aggregates, where they're going to put the topping layers on there, and this is very acceptable if it's okay with the standard. Quality control is an issue, however, because we have this variable material. We have non-uniform properties, parent concrete quality and its properties will affect that, the method of crushing and processing, and of course contaminants. And even a small amount of, for example, brick can have quite a big influence on the properties of the material. And so we really need to think of selective deconstruction, where we actually take out the concrete, or the demolished concrete at source, rather than as a mixed waste. That results in reduced contamination and improved consistency. So QC, or quality control. Now here are some standards just to show you what is available for the use of recycled aggregates, and there are a whole series of countries given there. Looking at India, you can see that for non-structural concrete, up to 100% of both coarse and fine aggregates are acceptable. In reinforced concrete, at this stage, only 20%. In plain concrete, 25%. On the other hand, if we go to the Netherlands, you can see, or South Africa, there we're a little bit behind, only 20%. But in the Netherlands, you can use up to 100% of both coarse and fine. And clearly they've made great progress here and know how to beneficiate and use their material to the greatest extent. You go to other countries, Germany and so on, Australia, Hong Kong, right down to Switzerland. Again, the picture is mixed. Sometimes only low values, but in other cases, you can go up to even 100%. And here, again, quality control is crucial to the use of these materials effectively. So standards are useful, of course, but they can also be restrictive. They can limit things when they don't need to be limited. And therefore, a performance-based approach is needed to fully exploit the properties of RCA. What about the prospects of the use of this material? Well, the overall regional or even national situation should be in focus, considering other possible uses. What we need to do here is to optimize the entire cycle, not just the concrete cycle. For example, it's not necessary that recycled concrete aggregates must go back into concrete. As I've explained, they can go into other uses. And so one really needs to take a regional view of these things. In other words, look at a whole region, see where materials are needed, see where one can replace other virgin materials with this material if it's not likely to be used in concrete. And in that way, one can optimize the use of these materials and achieve the lowest possible environmental impact. That's an important fact. And as I said, considering that the largest amount of cement in the developing world is used in brick and block production, there are vast opportunities for use of recycled aggregates there. Newer technologies also, such as the loose selective crusher, may allow much more efficient use of CDW. Is the loose crusher. Here you feed your concrete rubble in there, and then there's a process of crushing and through air separation where the fine material is moved up and the coarse material is moved down, one can get a classification of materials immediately, and actually the particle shape and the removal of the adhered mortar is very efficiently done. This is based on this reference over here that you can pick up if you wish. So these are the challenges then. First of all, the low usage in industry, especially in developing countries. This needs to turn around, and this is largely because of lack of incentives for waste management. But we've seen, for example, in Cape Town, how that can be rapidly turned around. Ignorance amongst built environment professionals. The first reaction when you suggest the use of this material is, well, I'm not sure, is it going to do the job for me? Because there's simply lack of knowledge or there is ignorance. Low landfill costs contributes to this, and lack of up-to-date technical standards, and that ever-present material variability that I have referred to. But there are prospects indeed. There is a suggestion that over the long term, the building obsolescence may reduce, but there is a tremendous stock of aged structures that will still need demolition in the next decades. And so this material will be around for literally decades to come, and we must make the best possible use of it. Also, pressures are likely to grow to recycle entire buildings by repurposing them rather than demolition. And this is where I love to use the example of the old grain silos in the Cape Town harbour. Here they are here. These are about 100 years old, or they were 100 years old about 10 or 15 years ago when they were repurposed. And you can see the sort of damage due to corrosion and spalling of these structures. Obviously, they're in a marine environment. You would expect that. The question was, should they demolish or should they repurpose those structures? And the decision was to repurpose them. And you can see the effect here with the finished product. In fact, this section now is the Zeitz-Mocker Art Museum, a modern art museum, which is very popular with visitors. And this is a very expensive boutique hotel where I could certainly never afford to spend a night. But you can see that it's turned into a very attractive structure that, as I said, attracts many people as visitors. And even more so because when you get into those silo structures, you see that they've cut away the old silo walls like this and created a very aesthetic interior for the art museum with proper lighting and so on. You can see the effect is actually quite stunning. And so he has a really wonderful example of how old structures can be repurposed and demolition can be reduced. I want to thank you for your attention. Merci. Nandri. And also then publication here, the recycled concrete aggregates and their influence on concrete properties. There was a collaborative venture by IITM, University of Witwatersrand and University of Cape Town, and anybody who would like a copy of this simply needs to get hold of me at that address and I'd be happy to make it available to you. Thank you very much for listening.